Welcome to this session on Azure SQL Database Serverless. My name is Morgan Oslake. I'm a program manager at Microsoft on the Azure Data Engineering team. I'd like to begin this session by reviewing what Azure SQL Database Serverless is, and then move on into a discussion about when and how to use it in order to best optimize price and performance, as well as reveal some insights about how serverless works under the hood. When customers begin their journey into Azure SQL PaaS, one of the first decisions that's made is the choice in deployment model between SQL Database and SQL Managed Instance that best aligns with their application scenario. Managed Instance provides a very high degree of application compatibility with on-premise SQL Server implementations. And so it lends itself quite nicely to lifting and shifting into the cloud. It minimizes the amount of application rewrite required, if any, and so is ideally suited for those kinds of migration scenarios. SQL Database is ideally suited for cloud-borne applications, and the single database option within that deployment model provides the greatest degree of management simplicity among all of the deployment models across Azure SQL PaaS. Elastic pools are an extension of single database and allow for multiple databases to share from the same set of resources in order to help reduce costs. Also, certain SaaS applications may benefit from elastic pools if they require database isolation on a per tenant basis. Serverless is supported in the single database deployment model. The next decision that's typically made in the onboarding journey is the choice in service tier. One way to think about service tier is it's your opportunity to specify the storage architecture for the database. So the amount of space the database requires, the kind of I/O performance characteristics that it requires are wrapped up at a high level in the service tier. But beyond that, the storage architecture is also very important in terms of the kinds of business continuity choices that are available. So, for example, high availability and disaster recovery requirements are often fit into the context of the service tier selection. The general purpose service tier provides a single compute instance with remotely located data relative to where the compute for the database is actually running. The business critical tier, on the other hand, provides a primary replica for the compute instance, as well as 3 secondary replicas for even greater high availability. And the storage in the business critical tier is co-located on the same machine as where the compute is running, which allows it to provide superior I/O performance. And then the hyperscale tier sits somewhere in between these two. It allows customers to specify the number of replicas that are appropriate for their particular HA goals. It also has, as part of its design, a caching hierarchy that is a blend between local storage and remote storage. And so its I/O performance characteristics tend to fall between the general purpose and business critical tiers. And then once the service tier is selected, the next choice that's often made is in the compute tier, where the choices branch between provision compute and serverless. You can think of provision compute as providing a fixed amount of resource for a fixed price. Now, the compute tier, beyond just the place where customers can specify the amount of CPU, for example, they need, or the amount of memory they need, uh, is where crucial decisions are made in terms of what kind of scaling is expected, what kind of compute scaling is expected of the database. Serverless is currently supported in the general purpose tier, but we'll have a little bit more to say about plans for that towards the end of the session. Before discussing what serverless is, it's useful to first step back and consider some of the challenges facing developers and DBAs when price and performance optimizing their workloads. So consider a typical scenario of an IoT application with a centrally managed database that collects rainfall data from thousands of geo-distributed weather stations, as well as exposing endpoints for users to connect to in order to run analytics scenarios against that data, as well as generate reports. Now, you can imagine that when the weather is relatively calm, usage on the database is relatively low, but that when a storm system passes through, the usage on the database can increase rather suddenly and to very high levels of compute. The key point to emphasize in this example is that the workload demand on the database is unpredictable, both in terms of its amplitude and timing. And this can present DevOps challenges in terms of how best to right size the compute for your database in order to achieve your price and performance goals. One option is to provision a sufficient amount of compute to accommodate peak workload demand. But then given this usage profile, where the peaks are often followed by somewhat lower idle usage periods, this can lead to wasted resources and ultimately higher costs. On the other hand, you can decide to provision an amount of compute that matches the average utilization over time. But then, of course, during peak periods, the database will be undersized and suffer from poor performance. If the database is already in the cloud, then you can take advantage of cloud elasticity and rescale the database, but this tends to lead to increased development costs as well as added operational complexity. So this scenario presents the kind of problem that serverless is intended to solve. Serverless essentially provides two kinds of scaling capabilities. The first is its ability to automatically scale over a range in compute that's indexed by a minimum and maximum number of cores corresponding to a range in memory, which is configurable by the customer. And so whatever the workload demand of the database is, at any point in time, the service is able to automatically scale the resources in order to satisfy that workload demand within this compute range that the customer is able to specify. The second scaling capability in serverless is automatic pause and resume. So here, if the database is idle for a sufficiently long period of time, called the auto pause delay, which is configurable by the customer, then the service will automatically pause the database, and the database will remain in a paused state until workload activity returns, at which point the database is automatically resumed. In terms of billing, serverless charges just for the amount of compute that's used on a per second basis across both memory and CPU dimensions. And then when the database is paused, and because we've terminated the underlying compute, we're allowed to sort of pass those cost savings along to the customer and only charge for storage. Now, this billing picture is to be contrasted with the provision compute tier, where the costs are based on the amount of compute that's allocated, which is a customer choice, and independent of the usage of that compute. And the bill is run on an hourly basis. So here in this example, in the picture on the right, I have a serverless database that's configured with a minimum of 1 vCore and a maximum of 8 vCores. And this jagged orange line represents the utilization of the database over a 24-hour period. And you can see that when that usage falls between the min and max number of cores, that the amount of compute that's billed is exactly equal to the amount that's actually used. That's represented by the green vertical bars here. But that as you move later in the day, say around the hour of 5 in the afternoon, all the way through the end of that day, the usage on the database drops below that minimum amount of compute, but that minimum amount of compute is still billed. And that's true until the database in this example transitions through an idle period for an hour that was configurable in terms of the auto pause delay by the customer, at which point it enters the pause state and that compute is no longer charged. So the charge for compute when the usage drops below minimums is really a result of the fact that we still have that compute provisioned in the background in order to provide some degree of performance responsiveness when workload activity returns. Outside of these scaling and usage-based billing benefits, serverless provides essentially the same PaaS manageability benefits as the provision compute tier. So high availability is built in, backups are automatic as well as updates. There is built-in machine learning that provides performance tuning recommendations as well as recommendations for various security-related optimizations. The kind of customers using serverless really run the full spectrum across vertical industries. So, this list is showing customers that are using SQL DB serverless today. There are financial sectors represented here, energy sectors, retail, education, transportation. The list goes on. What I'd like to do next is shine the spotlight on a specific customer. Icertis. So Icertis provides contract management services in the cloud for their own customers. They manage millions of contracts for their customers across nearly 100 countries around the world. Now, as the Icertis business continued to grow, it became increasingly challenging for them to predict their customers' usage patterns. And so this led to more and more inefficiencies in terms of how they were right-sizing resources for their database. And the response was natural, and to build move in a direction of adding more and more automation to those rescaling workflows. But they still found they needed to preemptively scale up, which prevented achieving the kind of price optimizations that they were seeking. So, for example, instead of scaling up at 8 o'clock in the morning, they needed to start scaling at 6 a.m. instead. And there were a couple of reasons for this. First, it was a hedge against the inevitable uncertainties in their customers' usage patterns. And then second, they needed to account for some variability in scaling times to avoid being undersized during usage spikes. So as they began to move their databases, migrate them from provision compute where they encounter these problems into serverless, that allowed them to begin to unwind some of these investments in their own automation and ultimately achieve a reduction in their costs on the order of 70%. But just as important to them as the reduction in their Azure costs was the fact that they were then able to free more development and DevOps resources to concentrate on adding business value instead of being having to concentrate on performance and capacity management related functions. When determining whether or not serverless is a good fit, it's crucial to understand the usage pattern of the database. So if the database is intermittent and unpredictable in terms of its usage and has a relatively lower average compute utilization over time, then it tends to be a better fit for pricing reasons alone. So imagine a pattern where the workload is relatively idle, but has these periods of points in time that are punctuated by high bursts in compute activity. Those tend to be a good fit for serverless. Also, if you have databases that are already being frequently rescaled in the cloud, then in a sense, serverless should be considered by default. Serverless tends to provide higher fidelity in terms of the kind of scaling speed and cost savings that are possible relative to performing the scaling in the provision compute tier. And then finally, if you have a new database that doesn't have any usage history, then serverless can often be a good starting point. Otherwise, customers are often tasked with the challenge of estimating ahead of time what the anticipated usage profile of their database would be once it hits production, and then encoding that profile into a simulation tool and conducting, often expensive performance testing in order to help identify the particular sizing requirements for the database. But of course, that whole process is time consuming and often somewhat error prone and risky. So serverless can take help to eliminate much of that uncertainty since it will do the right sizing for you. And if it later turns out that for whatever reason, serverless isn't a good fit for, say, pricing or performance reasons, then it can easily be moved over into the provision compute tier. There's a very high degree of mobility that serverless confers in terms of entering into serverless or exiting from it. That said, serverless isn't a panacea. It's not appropriate for every kind of usage profile. There are certain anti-patterns to take into consideration. So for example, if the usage on the database is more regular, perhaps it's more predictable, and has a higher average compute utilization over time. And we'll come back to making these notions of lower and higher compute utilization a little bit more precise later in the session. If that's true, then provision compute is often a better choice for pricing reasons alone. Also, it's important to take into account if the database happens to be particularly sensitive to performance trade-offs that can occur as a result of scaling. After all, serverless is constantly allocating and deallocating resources, both while it's auto-scaling as well as when it goes through pausing and resuming cycles, and invariably leads to or presents customers with a situation where the database needs to go through a warm-up period in order to sort of reestablish the performance that it had prior to those resourcing deallocations. And then finally, if you have multiple databases, maybe you're a SaaS ISV with an application that contains tens, hundreds, or even thousands of databases. If those databases can be consolidated into elastic pools, then elastic pools tend to confer better pricing optimization. In simple terms, elastic pools provide a much better compression of usage across multiple databases per unit of compute. Onboarding to serverless is very straightforward and generally follows the patterns for provision compute. So here I'm showing a PowerShell commandlet and highlighting the four parameters that distinguish creating a database in serverless versus provision compute. So the compute model needs to be specified as serverless, and then these three configuration parameters that we've discussed: the minimum number of cores, max number of cores, and auto pause delay. It's much the same story for existing databases that you'd like to move into serverless. Essentially the same API signature. And by the way, if I presented examples from CLI or REST APIs, they would also follow very similar patterns. It's worth noting that no application is required when moving an existing database into serverless. That said, if the database has auto pausing enabled, then it's crucial that the application have connection retry logic implemented. And we'll talk a little bit more about that, reasons why, later in the session. So with that, I'd like to first demonstrate onboarding into serverless. So here I'm showing the Azure portal and a logical server that contains 6 databases. Many of these databases are serverless, and some of them are paused. But what I'd like to do is create a new database in serverless. So I'll create the button called plus create database. And this will bring up a page that's largely pre-filled with database metadata. And so all I really need to do at this point is specify the database name. Let's call it MyDB. Click Configure Database. And then you'll see that the workflow is defaulted the creation of this database into the general purpose tier. And I have a choice to create it in either provision compute or serverless. So I'll select serverless. And next what we'll see are these 3 serverless configuration parameters: max vcores, min vcores, and auto pause delay. So I can make adjustments to the max number of cores, pick the number of cores that the serverless database will be able to scale up to, all the way up to 40 cores. I can also make adjustments to the minimum number of cores. And again, I may want to make adjustments to the minimum number of cores because that's a setting that's respected by the service that will never scale below. So if I have certain performance requirements that would benefit from a slightly higher minimum number of cores, I'm free to configure that here. And you may have noticed that when I made adjustments to the maximum number of cores, that also influenced the range of memory that's available for the database. Next, I can make adjustments to the auto pause delay. By default, auto pausing is enabled. I may want to, for example, increase the auto pause delay to avoid, let's say, pausing during the lunch hour of a work week, so that users of the database, when they come back from lunch, don't need to incur the performance penalty from the compute warming up after the database has been resumed, but still at the same time be able to benefit from pausing and resuming at night and on the weekends. So maybe I might make an adjustment from 1 hour to a little bit longer than that. On the other hand, if my database is particularly sensitive to the performance impact from compute warm up, then I can disable auto pause entirely and still benefit from the ability to automatically scale the database over this compute range and only be billed for the amount of compute used on a per second basis. So once I've made those selections, I can then just click apply, and within about a minute, the database will be deployed and ready to use. So when we set out to design serverless, we wanted to pay special attention to the relationship between CPU and memory usage. What I'm showing here is a scatter plot of individual databases. Each point in the scatter plot is an individual database. And on the horizontal axis, showing the average memory usage over a week-long period. And then on the vertical axis, the average CPU usage over a week-long period. And somewhat belying the way it looks here, there's actually hundreds of thousands of databases represented. So quite a large sampling of databases were used here from data centers around the world. And what you'll notice is that there are some databases that may require quite a lot of memory, but very little CPU. And conversely, there are other databases that may require much more CPU than memory. And then databases that have CPU and memory usage patterns for a lot of different points in between. So the key point to emphasize here is the independence between memory usage and CPU consumption across different databases. So we took that fact to heart in the design. Here I'm showing a picture of a serverless database that's configured with a minimum of 2 cores and a maximum of 16 cores, corresponding to a range in memory from 6 to 48 gigs. And so it could be the case that at one point in time, my database needs to perform, say, a table scan and is loading a lot of data from disk into its buffer pool. That operation will could consume quite a bit of memory, but generally perhaps not so much CPU. And then over time, the usage profile of the database can evolve, shift, and become more oriented towards computationally intensive operations, where much more CPU is required than memory. And so the key point to emphasize here is that whatever combination of CPU and memory is required by the database, the service is able and ready to deliver. And this is very important in terms of performance as well as price savings. Another way to think about this is that the memory to vCore ratio in serverless is dynamically adaptive based on the usage of the database. And that ratio ranges all the way up to 24 gigabytes per core, which is quite a wide range. Now, in terms of scale-up times, if the database, suppose at one point in time, is using 2 cores, but then in the next moment needs to suddenly scale from 2 cores up to 16 cores, then generally serverless is able to perform that rescaling extremely quickly and in under 1 second. There can be occasions where the rescaling time can take a few minutes if within our service internally we have to load balance resources in order to provide those resources. That's a much more rare occurrence. We'll talk more about that a little bit later in this session. Now, if I compare the picture of rescaling in serverless with rescaling in provision compute, it's a very different world. So in provision compute, the burden is on the customer to specify up front what the compute requirements are for their workload. So suppose I've determined that my database needs 2 cores. Then on generation 5 hardware, that database will also be allocated 10 gigabytes of memory. Now, one of the advantages of provision compute is that those 2 cores and 10 gigs are continuously allocated. There's no reclaiming and reallocation of resources under the hood. So you can think of provision compute as providing the database pristine performance dial tone. But on the other hand, that means that when the database isn't using either 2 cores or 10 gigs, those resources are still being charged. And then it could be the case, of course, that later in this database's life cycle, that it needs more than 2 cores and needs to be scaled up. So here again, the burden shifts onto the customer to first determine that the database is overutilized, what metrics to consider, what the utilization thresholds should be to inform triggering a rescaling operation. And then perhaps even more complicated than that is determining the amount of resource that the database actually needs that it should be scaled to. And so once that's been determined, the customer then needs to perform the rescaling operation, which can take on the order of a few minutes. And then at the conclusion, memory is reset, which represents some performance impact, and connections are always dropped, representing a brief disruption in availability. Now, this can occur in serverless as well, but again, it's a much more rare occurrence and only occurs if we need to load balance the workload in order to allow the database to achieve the scaling that it requires. So with that, next I'd like to demonstrate the speed of auto scaling in serverless. So here I've pre-created a database. And I can see active that it's in the general purpose tier. S stands for serverless. It's on generation 5 hardware. And it has a max vCores configured of 8. What I'd like to do is run 2 expensive queries. So each of these queries are selecting system objects and then materializing a large table and performing a nested loop join. So these are highly computationally intensive queries. I'm running two of them concurrently across different connections against the same serverless database. Now, in order to see how quickly serverless is able to scale up, I can look at the DMV for resource stats, which reports on usage across key utilization measures like CPU. So here I can see that I started this workload. I began running these two queries roughly at 36 minutes and 37 seconds. And that by 36 minutes and 57 seconds, so about 20 seconds later, the database was using almost 100% of all 8 cores. So this database scaled up from virtually idle usage up to its maximum number of cores in roughly 20 seconds. Now, it's quite possible that this database actually scaled up much more quickly, and we're only limited here by the resolution of this DMV, which is collecting and reporting on usage data just once every 15 seconds. So it's important to understand how memory management works in serverless, not just because of the performance consequences, but also because of the billing consequences due to the fact that serverless not only bills for CPU that's used, but also for memory that's used. So if, what's the common kind of memory in SQL, and how does it relate to how serverless manages it? There are dozens of different caches in SQL. There's the buffer pool cache, which contains data pages. There's column store, which of course contains column store cache entries. There are precompiled plans that facilitate faster execution of queries. And then there are query grants. Now, query grants are allocated and deallocated when before and after the queries are actually run. So they align rather nicely with the sort of serverless paradigm of allocating resources and then deallocating resources based on the usage of the actual usage of the database. That's unlike the case for these caches, where, say, for example, once data pages start loading into buffer pool, those cache allocations tend to remain allocated indefinitely. And so the size of the cache grows over time. And there's a good reason for this, of course, because this improves the performance of the database. If some time passes and that data needs to be reused because it's already resident and doesn't need to be fetched from disk or recompiled if it's a query plan, that's a better performance experience. And the memory is only released if the database becomes overutilized. Now, this presents a problem in serverless where the memory, of course, is billed. And if the database isn't using that memory, that can represent costs that are simply unacceptable. So in serverless, what we do instead, which is much unlike what occurs in the provisioned compute tier, is to deallocate memory or reclaim memory when usage on the database becomes low enough for long enough. So here we're really trying to strike the right balance between the impact to performance from deallocating memory and reducing costs versus keeping the memory around for better performance but increasing costs. So how does memory reclamation actually work in serverless? So every single cache entry has a timestamp, and on a periodic basis, we will analyze each cache entry and determine when it was last accessed. And if it was last accessed relatively recently, then it will be earmarked as a hot cache entry, and otherwise as a cold cache entry. And then what we do is we add up the size of all of the hot cache entries to come up with a total hot cache size, and compare that in relation to the total size of the cache itself. In other words, we compute the active cache utilization, which is really a measure of not so much how much memory is allocated, but more how much memory is being actively used. And if that active cache utilization falls below threshold, then the service sends a signal into the engine to reduce the SQL maximum memory target. Now, when that target is reduced, page evictions and cache entry evictions start to occur, but it's not necessarily the oldest cache entries that are evicted first. Instead, the principle is to evict cache entries that are the least costly to rehydrate. So for example, if I have a buffer pool page that was recently accessed, say within the last couple of minutes, and a plan cache entry that was compiled longer ago, then it's quite possible that when these evictions occur to reclaim memory, that the buffer pool page will be evicted first, because it's much cheaper and faster to fetch that page from disk and load it into cache than it is to recompile the query plan. So here again, we're trying to strike this right balance, this delicate balance between optimizing performance while at the same time attempting to optimize price. So how does pause and resume work in serverless? Suppose the database is in the online state. One thing that happens is that the service is constantly monitoring the number of concurrent sessions, as well as the CPU usage of the user workload. And if the concurrent sessions and CPU usage are both identically 0 for the length of time given by the auto pause delay, which was configurable by the customer, then the service initiates the pausing operation. The first step in the pausing workflow, the first major step, is to take a tail log backup to ensure an orderly shutdown, and then to detach database files before terminating the underlying SQL instance, and then ultimately stopping billing for compute. The length of time to pause the database is generally around a minute or so. It can range up to about 10 minutes. That latency, the variability in that latency is predominantly due to taking the tail log backup. And of course, the pausing latency ties very directly back into how soon those price savings can start to become enjoyed. Then the database remains in a pause state indefinitely. Now, it could be the case that the service needs to, say, perform an update. Under those conditions, it will automatically resume the database apply the patch, and then allow the database to be composed again. But most of the time, the only way in which the database resumes is if user activity returns. And this is usually in the form of a login. So when a login is received, the resuming workflow begins, at which point billing for compute commences, SQL database instance is launched, and then the database files are attached to it, at which point the database is online and able to process requests. The latency to resume is typically on the order of a minute. Sometimes it can take a little bit less, approaching 30 seconds. And of course, the resuming latency ties back more directly into the availability of the database and how quickly it can return to its prior performance. So now that we've had a discussion about how these different facets of serverless work, it can be useful to overlay that understanding on top of the architecture and then connect that back to the customer performance experience. The serverless is a three-tiered architecture. It has a control plane, which contains the gateway service that's responsible for connectivity. There's the management service as well that handles DDL operations like create and drop. And then sitting below the control plane is a data plane, which contain tenant rings, which are collections of physical machines that provide the compute to power the databases. And then below the data plane is a storage plane, which contains the database files that are located on remote solid-state disks. So now imagine that the database is in the pause state, and let's walk through a typical life cycle for it and overlay that on top of the architecture. So you can imagine that the first operation may be for the client to attempt to open a connection to the gateway. So as we said earlier, that first connection attempt to the gateway will necessarily fail, which is again why it's super important for the application to have connection retry logic wired into it. And then on a subsequent connection attempt, the gateway will authenticate the client and then transfer control over to the management service, which will then work in cooperation with the service fabric to identify a specific machine in a tenant ring that has sufficient capacity to handle the rescaling patterns for that serverless database. On that machine is a component called RG Manager that is performing constant surveillance of machine utilization as well as utilization of the individual SQL instances hosted by the machine. And if the RG Manager detects a bottleneck, then it attempts to resolve it locally. So for example, if there are two serverless databases that are sharing a subset of cores, and those cores become overutilized, then RG Manager will detect that condition and identify a cooler set of cores on the same machine that it can reaffinitize one of those serverless databases to. And that reaffinitization is a very fast operation, typically completing on the order of milliseconds, or sorry, microseconds even, and bearing virtually imperceptible performance impact to the database. Now, it can be the case that the machine itself overall is overloaded. If that's the case, then that's where the service fabric re-enters the picture and will identify a different machine in the ring that has sufficient capacity to absorb the rescaling operation for one of those serverless databases. And it will then orchestrate the repositioning of that database from the hot machine to the cold machine. That load balancing motion can take on the order of several minutes. And this is what we discussed before, can occur, but is a fairly rare event. Most of the time, the rescaling requests that are imposed upon a serverless database can be satisfied extremely quickly on the same machine with virtually imperceptible performance impact to the database. Now, in parallel to this sort of machine level resource management, within each serverless SQL instance, the memory manager is constantly analyzing its memory usage history and looking for opportunities to reclaim resources, as we've discussed, in order to pass those cost savings back along to the customer. So next, I'd like to provide some numerical details by way of example of how the performance in serverless compares to the performance in the provision compute tier. So we took a provision compute database with 4 cores and compared that against a serverless database with 4 cores. Otherwise, these databases are identical. They're both in the general purpose tier on Generation 5 hardware. And then we ran a OLTP cloud benchmark, which in terms of its read-write mixture has about 70% reads and 30% writes. The size of each of these databases exceeds the total amount of memory that is available to them. And the load on the database is across roughly somewhere between 200 and 300 concurrent users. And what we saw is that the throughput, the steady state throughput for each of the databases is virtually identical, 248 transactions per second. But one thing that's different is that the transaction latency for the serverless database is slightly higher than provision compute, 84 milliseconds in the 90th percentile as compared to 57 milliseconds. Now, this is largely due to the fact that the amount of memory that's available to a provision compute database for the same number of cores is slightly larger than the amount of memory that a serverless database can scale up to for the same number of cores. Then next, we looked at the latency for the serverless database to reestablish its steady state throughput, first after a full cycle of memory reclamation. So in this example, in this test, the workload was spun down at one point for long enough so that usage was low enough that the service was able to go through a full reclamation cycle, at which point we then relaunched the workload and are plotting here the time it took for the database to essentially rehydrate its caches. That warm-up latency was around 2.5 minutes before steady state throughput was reestablished at 248 TPS. We then looked at the latency to reach steady state throughput after resuming from a paused state. So here, where my cursor is placed, the database has just been resumed. And in that case, the warm-up period was longer, about 10 minutes. Now, of course, part of this warm-up period is due to the caches being rehydrated, as was the case in the previous test. But unlike the previous case, because the database was paused, and the underlying compute was completely terminated, there are additional initializations that need to occur, and only occur once workload activity actually returns. And that sort of represents the balance of the additional latency that was observed. So how to think about the pricing of serverless. One way to do this is to compare the serverless costs against provision compute costs. And one way to do this is to think about how much one core of provision compute cost for 1 hour. About 25 cents. Of course, it varies by region. In contrast, the cost of serverless for one core for 1 hour is about twice as much, or 52 cents for the hour. But that's only the case if the serverless database is using that entire core for the full duration of that 1 hour. If instead the database is say using half as much, say using one core for half as much time, then because serverless is billing based on usage, the costs come down by 50% or so to a level that's comparable to what it would cost in provision compute. So in other words, if the usage, both in terms of memory and CPU of the serverless database, on average over time, doesn't exceed around 50% or so, right? If it's or less than 50%, then serverless tends to be a better pricing fit. So how exactly does billing for compute work? At each second in time, the service is analyzing the CPU usage as well as the memory usage. And it then compares the two, and whichever is larger is the resource that's billed for that 1 second in time. Now, this naturally leads to the question of, well, how do you compare usage in CPU with usage in memory? They're different resources, the different units. So for billing purposes alone, we divide the amount of memory that's used, we rescale it by 3 gigs per core. So for example, if at over 1 second in time, the database is using 1 core of CPU and 6 gigabytes of memory, then we divide 6 gigabytes of memory by 3 gigs per core, which works out to be 2 cores of memory usage, which is larger than 1 core of CPU usage. And so therefore memory becomes the resource that's billed for that 1 second time. And then in the next second, that calculation is repeated, and it could very well be that CPU becomes the dominant cost factor. And so each of those vCore seconds that are measured can then be added up to come up with a total number of vCore seconds. And that's what determines the compute bill. And take the total number of vCore seconds and multiply that by the compute unit price, which is dollars per vCore second. Then you get a compute cost in terms of dollars, to which the storage cost is added to come up with the total cost for the database. So with that, I'd now like to demonstrate the kind of price savings that are possible serverless. So here we're looking at the Azure portal again, this time for a specific database that is in serverless and configured with a max core of 16. The chart in the lower left-hand corner here is showing its compute utilization over time. And you can see that it has, 2 or 3 bursting episodes where it's scaling up to 100% of all 16 cores, and then in the balance of the time, the usage is relatively idle. You can also see how that compute usage tracks closely with the chart on the right, which is displaying the number of vCore seconds that are billed. Now, if I'd like to estimate the compute cost for this database, let's say over a 24-hour period, then I just need to aggregate the total number of vCore seconds over that period of time, which is given by the metric displayed in the lower right-hand corner of this chart, 284,000 vCore seconds. So if I take 284,080 vCore seconds, and I know the compute unit price represented by dollars per vCore second, which is fractions of a penny, and multiply those two quantities together, I'll come up with an estimate for the total compute cost, which in this case is around $41. Comparing that against the price in the provision compute tier for the same number of cores, 16, the cost in that case over that 24-hour period of time is $96. So here, the price savings with serverless is around 50%. Now, it's important to restate that the reason why serverless in this case is less expensive than provision compute is because it has these bursty usage patterns where the lower average compute utilization over time is somewhat low, but it's still able to enjoy the benefits of scaling up to 16 cores when it needs to. In terms of roadmap, we have plans to support serverless in the hyperscale tier. As I mentioned earlier, it's currently only supported in the general purpose tier. And there are plenty of workloads that either have, say, storage requirements that exceed the limits in the general purpose tier, or I/O performance requirements that can only be satisfied by the hyperscale tier. We'd also like to continue pushing up the compute limits. We recently increased the compute limits from 16 cores to 40 cores in the last few months, and we'd like to continue making higher and higher compute limit choices available. We're making investments in pausing and resuming. For example, we'd like to lower the minimum configurable auto pause delay from 1 hour as it is currently to something on the order of minutes. Again, this is a length of time that needs to elapse while the database is idle before it can pause. And by lowering that minimum configuration choice from an hour to something on the order of minutes, we'll be able to give databases more opportunities to pass through pausing and resume cycles to enjoy even greater price savings. We're also making improvements in connectivity. We'd like to build connection retry logic into our SQL client libraries to relieve developers of that implementation burden. And then finally, we'd like to expand the range of high availability choices for customers to include support for availability zones. So in summary, SQL Database Serverless is price and performance optimized for single database workloads with intermittent, unpredictable usage. And it achieves that optimization by automatically scaling compute, automatically pausing and resuming, and then billing just for the amount of compute used on a per second basis. So for more information, I'd invite you to visit aka.ms/SQL DB_serverless. And with that, I'd like to thank you very much for joining the session. Please feel free to reach out to me with any questions, as well as stay on the call for Q&A to follow. Thank you.